All right, we have learned centripetal acceleration, centripetal force, and then for anything in circular motion, there's always a centripetal acceleration toward the center, always a centripetal force toward the center to keep this object in circular motion. This centripetal force, as I said, can be any force. It's not a new type of force. You don't need to draw a centripetal force on the free body diagram. You don't. You still draw all the normal forces we usually draw. Then you identify which force is the centripetal force. We saw an example last time with the car making a turn. In that case, the static friction force is the centripetal force. We set them equal. Then we find the maximum speed the car can have and still make the turn successfully. Now we're going to take a look at more examples. As I said, circular motion is very non-intuitive. That's why we want to practice that. But the laws are still Newton's laws we have learned. We're not using any new laws. So it's still the same laws, but we just apply them in circular motion. Let's take a look at the next question. If you have seen car racing, you should notice that the turns, okay, in car racing, they're always banked. That means they are not totally flat. They actually have an angle with the horizontal flat surface. Why is that? Because as we saw last time with the question, if on a flat surface, a car wants to make a turn, the centripetal force comes from the static friction force from the road, right? But the centripetal force, the static force from the road has a maximum value, and that value is this maximum static friction force equation we learned, right? And that's the only source of the centripetal force when a car is moving on a flat surface. But if the road is banked, then the friction force and then one of the components of the normal force from the road can also be centripetal force. So there are now two sources of centripetal forces. So the total centripetal force the car can get from the road can be larger than only this static friction force. So in that case, the car can make the turn with an even larger speed than when the car is moving on a flat road. Because now the total centripetal force it can get from the road is going to be a combination of the one component of the normal force and the static friction force. So that's what we're going to see in this question, okay? How can the component of static normal force become a centripetal force? Let's take a look at this question. So, okay, so that's a story. Race car ride drivers, they are able to navigate very sharp turns at very high speeds. And then, as I said, the normal force has a component. In this case, the normal force has a horizontal component that can act as a centripetal force. We're going to suppose the curve at a radius of 50 meters and a banking angle of 25 degrees. We want to find the, okay, so to make things simple, let's do this. What is the critical speed of the car that can make this turn without any friction force? So that sounds really weird. What does it mean like without a friction force? We just learned that there must be a static friction force from the road to keep the car in the circular motion. Let's draw a free body diagram, then we know what it means. So if it's a banked road, so I'm going to draw it this way. So this is the road. Okay, this is the horizontal, flat horizontal direction. Okay, this is a road. So the road has a bank angle with this horizontal. Okay, a banking angle 25 degrees from the problem. And now we're going to draw a back view. So we're looking at the car from the back. Okay, if you look at the car from the back, this is what you see. Right? The car is still moving in that direction, okay, away from me, but now I'm looking at it from the back. That's what I see. Now let's draw all the forces on the car. gravity down, right? What about the normal force? Normal force is perpendicular to the surface, right? So normal force must be in this direction. Okay, so there's a normal force. Now, how come the car can make this turn without any friction force? Because the normal force can provide some centrifugal force for the car to make this turn. Let's take a look at it. Now, if the car is making this turn, where the center? Okay, the center is still somewhere here, right? So the problem says the radius is 50 meters here. Some people may make that mistake. Some people, they would draw the center like in this direction. They thought, okay, this is the banked road. So the car is like the center is here. Okay, you should be careful. The car is still moving in a circle, in a horizontal circle. Okay, so words sound a little bit confusing. It's still moving in a horizontal circle. Okay, it just banked. Okay, so it's not like moving this way. The car is still, see, it's on a banked road, but it's still moving on a horizontal circle. In a horizontal circle, the center is still somewhere there, right? If you assume, okay, oh, the center is here, what would be the circular motion? The circular motion would be like this. You see? That's when the center is down there, okay? And the car is definitely not moving this way. The car is still making the turn in a horizontal circle, okay? Even though the car now has an angle with the horizontal, okay? So the center is still here, it's still moving in a horizontal circle, okay? But just the road is banked. That means the centrifugal acceleration is still in this direction, so it still needs a centrifugal force in that direction, right? Where is this centrifugal force? Now, if you break this normal force into x and y, now I'm going to still use the normal x and normal y, okay? The horizontal is x, the vertical is y. So I'm going to still use this as my x-axis, this as my y-axis. Now let's break this normal force, okay? If you break this normal force, you can see that it's going to have an x component, right? Because now the normal force is not straight up, it has an angle, so it will have an x component in that direction. It will also have a y component straight up, right? Now in this case, even without any friction, the car can still make the turn because the normal force can provide some centrifugal force, which is the x component of this normal force. So let's call this, to make it more specific, let's call it normal force x component, and this is normal force y component. All right? So in this case, you see, you don't need to draw centrifugal force on this diagram. That's why this is going to confuse you. Some people, they draw another centrifugal force. So it looks like there are two forces on this car in that direction. No, there's still one force in that direction, the x component of the normal force. But in this case, the normal force is, the x component of the normal force is a centrifugal force. Now you see that even it doesn't have to be a whole force. It can be just a component of the force, right? Okay. Now I'm going to set up, and in this case, you see that that's going to be only a certain speed. The car can make this turn without a friction force. Because you can solve this equation, find a very specific speed. So only the car moving at that speed can make this turn without a friction force. If the car is making this turn with a different speed, you will have the static friction force get involved. Now let's first find this critical speed, right? So let's forget about the friction at this moment. If these are only two forces on it, I break them into x and y, so now I can set up Newton's second law. See, I'm still using Newton's second law. I'm not using a new law. It's still the laws of motion I learned. If I use Newton's second law, I would do net force in x direction, right, equals mass times acceleration in x direction. And then do the same thing in y direction. Net force in y direction equals sum of all the forces in y direction equals mass times acceleration in y direction. Then let's complete these two equations. So I'm going to find all these components in x direction, put it on this left hand side. Find all the y components, put them on the left hand side of this equation. X component, easy. There's only one x component, which is the normal force x component, right? Now you're going to equal that to mass times acceleration. So a lot of people, they would say, oh, the car is not moving in this direction, so the acceleration must be 0. You should be careful. It doesn't have any acceleration, normal acceleration we would find, but because it's in a circular motion, there's a very special centrifugal acceleration toward the center. So even before I set up x and y, I know there's always acceleration in that direction, for sure. Now you call this direction your x direction, so that's going to be the acceleration in my x direction, right? So the x direction shouldn't be 0. If you put a 0, it doesn't make any sense, right? If you put a 0 here, you see the x component equals 0. That's going to make the normal force 0. That's going to make this force 0. It doesn't make any sense, okay? So you will have m times the centrifugal acceleration, because now the acceleration in x direction is not a number from the problem like 5 meters per second squared. It's just going to be the expression you plug in, which is the expression for the centrifugal acceleration. So that's the difference between circular motion and straight line motion. In a straight line motion, the problem may tell you it's 5 meters per second squared or things like that. In a circular motion, you should be careful. Even if the object is not moving in that direction, but if that's the direction of the centrifugal acceleration I call x, that's going to be the acceleration I plug in x direction, v squared over r. Okay, so we have completed the equation in x direction. Now let's switch to y direction. Y direction, there are two forces, right? The normal force y component up, so that's going to be positive to me. Gravity down, that's going to be negative to me. Now, what is the acceleration in y direction? First of all, it's not moving in this direction. There's no normal acceleration. Is the center in this direction? Is the centrifugal acceleration? Is there any centrifugal acceleration in this direction? No. So there's no acceleration at all in this direction. Then you can put a 0, right? So you should be careful. Once we have learned circular motion, when you're looking for the acceleration to plug into Newton's second law, you should watch out. In addition to the normal acceleration we would find when something is just moving in that direction, there's always centrifugal acceleration. And once you set up your x and y, you're going to make sure that centrifugal acceleration is in your x direction or y direction. That's going to be the acceleration you plug in that direction. Okay, so it's not going to be a normal acceleration. It's going to be the expression you plug in. Then, okay, I have finished these two equations. Now, don't forget what we're doing. We want to find this speed, right? So this speed is going to be a very specific value. So only the car moving at that critical speed, then no friction is needed. It can just make this turn with this x component of this normal force. It can do that. How do I find this v? Well, if I have the normal force x direction, so I can find that. Right? I just rearrange this equation, I will find the v in terms of this guy m and r. And then the r is given, okay? But the m is not given, so I'm missing a lot of things. We have another equation we haven't used. So let's try this equation. This equation can tell me one thing at least. The y component of the normal force equals gravity. Okay, so that's also intuitive, right? Because one component up, one component down, nothing in this direction. So of course these two forces, they're gonna cancel out exactly. But I want f and x, right? If I have ny and then I have f and y here, so I can just plug it in. But I need f and x on this left hand side so I can rearrange this equation. But f and y and f and x, they are definitely connected. Right? They are just x and y components of the same force. So there must be some connection between them. So let's see how I can find the connection between them. So this is f and x. This is going to be f and y if I look at this right triangle. So if I have an angle in this right triangle, I can definitely connect them. So that, again, I'm going to transport this theta angle to this right triangle, right? So how do I do that? Well, again, there are different ways to do that, right? So what I usually do, say if I extend this line, okay, if I extend this line, then I would get this angle. What is this angle? Well, take a look at this right triangle. So this is the right triangle, right? If this is the right triangle, because this is the perpendicular line, this is the incline, right? This is the normal force is perpendicular to the surface. If this angle is theta, this angle is going to be 90 minus theta, right? Because this is a right triangle. And if this is 90 minus theta, this angle must be the same, 90 minus theta, right? Because they are the same angle, the same two lines, right? The normal force line and the horizontal. Normal force line and horizontal. So this angle must be 90 minus theta. If this angle is 90 minus theta, what is this angle? Well, again, this is right triangle. If you call this angle 90 minus theta, this angle must be 90. Because all these three angles added together should be 180, right? So this angle is theta. Now I do have a theta angle. So I can use theta angle to connect x and y. So for example, this f and x is opposite to this theta angle. This f and y, which is this side, is adjacent to this theta angle. So if I want to use tangent theta to connect them, what do I get? I should get opposite over hypotenuse. So that's going to be x over y here, and this question. Again, a lot of people say, well, isn't tangent theta y over x? Don't remember these shortcuts. The problem can give you a different angle, right? It's not there's always a theta angle from the problem. Whenever I use theta angle, okay, tangent theta equals y over x. In this case, because we transported this angle to this right triangle, and turns out this angle is the theta angle given the problem. So if I want to use this theta angle, I will write it this way, right? So now you see that, oh, that's how I'm going to connect f and x and f and y. If I know the expression for f and y, then I can rearrange this equation and then get an expression for f and x. And if I get this expression, I can plug it into this equation. And you're going to see that even the mass is going to cancel. Remember, we're missing mass from the problem. But once you plug it in, you're going to have mass on both sides. You're going to cancel mass. So you don't need the mass. That's what I usually say. Do algebra with the symbols. It's better than doing algebra with the numbers. Okay? It may be... some people may not be used to that, but once you get used to working with the symbols, okay, it's definitely going to make your algebra simpler, because you may be able to cancel a lot of things. Okay, now you can stop, pause the video and finish the algebra to see what expression you can get at the end. And then once you have the expression, you can plug numbers in to find the velocity, the critical speed. All right, what is the number you got? So first of all, if I rearrange this equation, what do I get? I get normal force y component tangent theta. It's going to be f and x. And then normal force y is mg, right? So I can replace that with, this equation is going to become mg tangent theta equals mv squared over r. And then the little m and little m cancel. So the v in this case is just going to be equal to g tangent theta times r. Now I can put numbers in. The only numbers I need are going to be the theta angle, is the radius, and these are the two numbers the problem gives me. So if you put all these numbers in, what do you get? 15.1 meters per second. So this is a very special speed. If the car is making this turn at this speed, it doesn't really need any friction from the road. The x component of the normal force can be the centrifugal force. So the car can make this turn very successful. And of course, this is the only speed the car can make this turn without any friction force. If the car makes this turn with a different speed, then the static friction force will be there, right? Because if it has a different force, then these two numbers, they're not going to be equal. You see that if f and y equals mg, this f and y is going to be fixed. This number is going to be fixed. If you change this value on the right hand side, this is not going to be equal. So the normal force is going to be the total centrifugal force. Then you need some static friction force to get the total centrifugal force. So you still have the centrifugal force equals to mv squared over r. Now let's take a look at a case. Say, if I want this car, now I'm going to redraw it. So let's say, okay, I'm going to drive this race car with a speed even larger than this. I can still make this turn, but then I'm going to need friction and the normal force in order to provide the centrifugal force. So the question I want to ask you is this. In this case, what would be the direction of the static friction if the car is making this turn with a speed larger than this? So this is not very intuitive, okay? This is not very intuitive. Again, this is a perfect example. You shouldn't always trust your intuition. Your intuition doesn't always lead you to the right answer, especially if things are complicated, okay? So first of all, the static friction, first of all, it's going to be static friction. We know that. Secondly, the friction can only have two options, right? Either this way or that way. This way or that way. Now, the center is still here. So the centrifugal acceleration is still in this direction for sure, because it's still making a centrifugal horizontal circle. If the car is moving with a speed larger than this, so I would still have this equation. The net force in x direction, it's going to be mv squared over r. So if I only have the normal force in x direction, so that's not going to be equal to this, right? Because we found that if only normal force is only and no friction force, this number is going to be determined by the gravity. So the normal force x component is going to be determined by this. So it's going to be a number. It's not going to change. But if you increase the velocity on the right hand side, you need something on the left hand side to make sure this satisfies Newton's second law as well. So it's going to make the turn, right? So if the speed is larger than that, so it needs more centrifugal force in this x direction, and then so that's going to help you figure out the direction of the static friction, because the static friction can only be either this way or that way. Okay, but it's really hard for you to tell the car is attempting to move this way or that way. It's really hard for you to tell. So this is not a very complicated case. We're going to use the law. So see that which direction is going to provide you some component in that direction to get you more centrifugal force. Obviously, it's going to be this, right? So if the car is making this turn with the speed larger than this, it's going to need a static friction force actually in that direction, very, very non-intuitive, right? In that direction, because the friction force must be parallel to the surface, right? So it cannot be in that direction. That doesn't make any sense. You don't have a friction from a surface in that direction, because that's not parallel to the surface. Static friction force is going to be parallel to the surface, so either this way or that way. We figured that we need more centrifugal force in that direction. That's still the center. Only a friction force in that direction can provide us more centrifugal force in that direction. If you say the static friction force is in that direction, it's going to actually cancel some of the x component of the normal force. It doesn't really help. Okay? So that's how I figure out when the car is moving with a speed larger than this, what's going to be the direction of the static friction force. And in that case, you can still use Newton's second law to set up like the two laws, the law in x and y direction, and then solve this problem, right? It's just going to be a little bit more complicated than this, because now we're going to have a third force, but you can still break it into x and y and then set up the Newton's second law in x and y and then solve a problem like that. All right, so that's this problem. So one question I usually get in this part is this. So this is actually a very good question. Some people, they would say, well, I remembered you said that on the incline, the best coordinate is going to be this and this. right? So why didn't you use this as your x and this as your y? Why did you still use the horizontal and vertical as your x and y? So this is in contradiction with you said. Well, this is a special case. So first of all, you use this coordinate system or this coordinate system, you always get the same answer. Physics doesn't depend on the coordinate system you pick. So either this or this, you will always get the same answer. Now, what is the reason we usually pick this coordinate system when we are on an incline? We said that's going to make us break less forces, because most of the forces are going to be on the x and y if you pick this as an x and y. So the only force you usually need to break is gravity, right? Because if you pick this x and y, gravity is not in x and or y. You can break it in x, y. So that's going to help you break less forces. That's just going to help you simplify the algebra you're going to do, right? It's not going to really be a new theory. You can still use that and solve any problem on an incline. Now let's take a look at this question. We just figured that if I use this coordinate system, the only force I need to break is going to be normal force, right? If I use this horizontal and vertical, and we did that. We broke it into x and y. Now, so there's only one force I need to break, right? Normal force. If you use this, how many forces do you need to break? You're going to break gravity actually, right? Because you're going to have gravity in this direction. But you're going to have normal force in the y direction, so you don't need to worry about normal force. But there's another vector in this problem, right? You would say, okay, looks like this and this, they're going to break the same number of forces at 1. Remember the acceleration is in this direction, right? The center is here. The car is still making a horizontal circle. If you want to plug the acceleration into this Newton's second law, you're going to break this vector into x and y. Because this is neither in x or y axis. You would have to break this a into ax and ay if you want to use this coordinate system. So there's nothing wrong to use this coordinate system in this question. You actually need to break two vectors. One force, sure, but there's an acceleration you also need to break. And we usually don't break in acceleration. I'm more used to breaking forces. I don't really like breaking acceleration. So if you want me to compare this coordinate system and this coordinate system in this question, I would always put the acceleration in one of the axes. So I'm not going to, I may break more forces, that's fine, but I don't like breaking acceleration. All right? So there's nothing wrong if you want to use this coordinate system, but you just need to break two vectors, and one vector is the acceleration. And we usually don't break acceleration. You can do that, okay? There's nothing wrong, all right? So that is why we use still the horizontal and vertical in this case. So when I pick a coordinate system in this part, especially if there's a centrifugal acceleration, I would always make sure the acceleration, the centrifugal acceleration is in my x or y. Then I will pick the best coordinate system. Okay, so it's a little bit special. But again, the physics, the answer doesn't depend on the coordinate system you pick. You pick any coordinate system, as long as the x and y are perpendicular, you solve the problem, you always get the same answer, the right answer. All right? Now, let's take a look at the next question. So we're going to again do some more practice on circular motion, because this is not that intuitive. So in this question, we have seen that the normal force, or more strictly speaking, an x component of the normal force is the centrifugal force. As I said, any force can be centrifugal force. Now we're going to take a look at a different example. In this example, this is a conical pendulum. So a normal pendulum would be this, right? You attach like an object to a string, you just swing it back and forth. That's a normal pendulum. A conical pendulum is this. I don't swing it this way, I would swing it in a two-dimensional plane, like this. Okay, so this is still a pendulum, but it's swinging in a two-dimensional plane instead of like one-dimensional. Okay, so that's called a conical pendulum. So we're going to take a look at this. Now, let's see. So let's draw it out. So this is the string, and then what we want to do is this. We want to find the, if the ball revolves with a constant speed in the horizontal circle, so like what I just did, right? This ball is going to be moving in a horizontal circle, okay? And I want to find the speed of the ball. If I know the mass of the ball, 3 kilograms, the string has the length 0.4 meters, and the radius of the circle is going to be 0.24 meters. Okay, so let's take a look at this. So this is the vertical line, and this radius, I know from the problem, that's 0.24 meters. And this length is 0.4 meters. Now this is the pendulum bob. I want to find the speed. How do I connect the speed to everything in this question? The centrifugal acceleration has speed in it. So if I can connect the centrifugal acceleration to all the numbers I have in this problem, I can find expression, I can find the speed of the ball. How do I connect the centrifugal acceleration to all these things? Well, that's still Newton's second law, because Newton's second law has force and acceleration in it, and then the acceleration, and this question is going to be centrifugal acceleration. Now let's draw all the forces, right? I still need to draw the forces on this object. So this guy has a tension, has a gravity, and then that's it, right? This is not a line, right? Oh, there's nothing between them. That's just a radius I draw. So there are two forces on this guy. So I'm going to redraw it here so it's not confusing. Gravity, tension. Now I want to find the speed, right? So where is the center? The center is here. This is the center. So there's a centrifugal acceleration toward the center always. But I'm not going to draw the centrifugal acceleration on the free body diagram because I don't want to make this look like a force. Again, you don't draw centrifugal force on this. You don't draw centrifugal acceleration in this free body diagram. You don't. Otherwise, you're going to confuse yourself. I know there's a centrifugal acceleration toward the center, okay? So I'm just going to remind me that's the direct direction of the acceleration of this ball right at this instant. Now I'm going to break everything into x and y direction, okay? So, okay, let's do this. So I know the acceleration. Let's draw it a little bit farther. Let's draw this tension a little bit shorter. Okay, so that's the center. This is the acceleration. I'm going to break everything into x and y. So again, as I said, I'm going to pick a coordinate system so that I can put my acceleration, the central acceleration, in the x or y, because I don't like breaking acceleration. So the coordinate system I'm going to pick is still going to be this. Okay, x and y. So now you see that I put the centrifugal acceleration in x direction, positive x direction. That means if I want to plug in the acceleration in x direction, I should use v squared over r. Okay, I shouldn't just use 0. So if I set up Newton's second law, what do I get? I will get this. Again, net force in x direction equals the sum of all the forces in x direction equals mass times the acceleration in x direction. And then do the same thing in y direction. Equals MAY. Excuse me. Then, okay, so if I use this x and y, I would break the tension into x and y components. So this is Tx, and then this is Ty. Now, okay, let's put all these components into these two equations. So I would get Tx, okay, so that's the only x component, equals mass times the acceleration in x direction. Again, it's not moving in this x direction, so it doesn't have any normal acceleration, but it's moving in a horizontal circle. So the center is here, there is acceleration toward the center. If I call this axis x-axis, that's going to be the acceleration I plug in v squared over r. That's the acceleration in x direction. It's not 0. If you put a 0 there, it doesn't make any sense. You're going to make the tension 0, which doesn't make any sense here. Now let's do things in y direction. Ty, positive, minus mg. And what is the acceleration in y direction? These are the two components in y direction. What is the acceleration in y direction? Nothing, right? It's not moving this direction, so there's no normal acceleration. The centrifugal acceleration is not in this direction, so 0. Absolutely 0. Now let's see. Don't forget what we're doing. We're trying to find the speed of the ball, so I'm still trying to find v. Again, if I have this tx, I can find this v, but I don't have tx. Take a look at the second equation. Maybe I can get something from the second equation. Well, if I rearrange this equation, I get this. Ty equals mg. I have ty here, but I need tx. Well, y and x, they can be connected because that's the components of the same force. Okay? So, does this start getting familiar? This is what we just did in the previous question, right? Okay, how do I connect this tx and ty? If I use the theta angle in this question, even though the problem doesn't give me the theta angle, it just draws this theta angle for me. That theta angle is going to be this theta angle, right? So that's the theta angle between the string and the vertical, and the tension is in this direction, it's parallel to the string. So the angle between the tension and the vertical is going to be this theta. And you can find this theta angle, right? This theta angle, if you want to find it, and this diagram, it's going to be sine theta equals 0.24 over 0.4. So you can do theta angle equals sine inverse 0.24 over 0.4. Okay, so that's how you find the theta angle. And then, if I have this theta angle, how do I connect the y and x? That tx is opposite to this theta angle, ty is this side, adjacent to this theta angle. So if I use tangent theta, I would get opposite over adjacent, so that's going to be tx over ty. Right, now you see that I can connect them. I will find an expression for tx and use this ty. I plug it into the first equation, rearrange this equation, I should get this v. Okay, now I can finish the algebra. Again, does this look familiar? This is what we did in the previous question, right? So now you finish this algebra, what is the number you got? This dx, again, is going to be ty tangent theta. And then this is going to give you, so ty is mg, so it's going to get mg tan theta equals m v squared over r. You cancel little m, what do you get? You get v equals g tangent theta times r. You plug the numbers in, right? You find theta using that two length. You put all these numbers in. What is the number you got? 1.3 meters per second. Now if you compare this answer with this answer, oh, they're exactly the same. Why? Because even the free body diagram is the same, right? See, you have a normal force in that direction, gravity down. Now I have a tension in that direction, gravity down. So even these two equations we set up are the same, right? So x component equals m times v squared over r. Y component minus mg equals 0. And we set up exactly the same equation here, right? X component equals m v squared over r. And y component minus mg equals 0. So of course, pretty much what we did is just replace this Fn with t. Everything else is the same. Everything else is the same. So that's why at the end you will get this conclusion. And this is also a very good example where you can see that these two problems, they are totally two different stories. The first question we did, that's like a race car on a banked road. The second question we just discussed is a conical pendulum. Two different stories, totally different. We use the same theory, But it turns out these two questions, even the algebra, the Hilbert diagram, the vector analysis, everything is the same. Even the final expression is the same. So that's the idea. That's what we're doing in physics. We always use the same theory, okay? We always use the same theory to set up different stories. The laws and theory are always the same, but the stories can be really complicated, can be totally different, but I'm going to always apply the same laws. Set up Newton's second law in this part, circular motion, it's always going to be Newton's second law. You set it up, you rearrange this equation, you can find things you need. Again, some people, they would say, oh, I see this conclusion for both of these two questions. Do I need to memorize that? No, you don't. There's no point doing that. Even if you memorize this, how do you know in what stories you're going to apply this theory, this conclusion? You don't know, right? If I give you a new story, how do you figure out that I can just write down this conclusion and plug numbers in, right? You don't do that in physics. We don't memorize these special conclusions from all these problems. I've said it many times, so that when I see a similar story, I'm just going to write it down and plug numbers in. That's not what we are doing in physics. So you don't need to memorize this. No, there's no point doing that, right? We just use these two equations as an example to show that you always use the same theory, the same laws for questions in this part. And so far, the only laws we have been using over and over again is going to be Newton's second law. Right, so next time when I see something moving in circular motion, I will still set it up the same way and then rearrange this equation and then find things I need. The problem may ask you to find different things. The story can be totally different, but the theory and the laws are always the same. That's what we're learning in physics. Okay, I'm gonna stop here for this video.